Your goal is to basically perform this in a circle fitting. So what is this circle fitting that I'm doing here? I'm saying, okay, you have two dimensions, x and y, okay? I can basically manipulate the x and y's in a way that I can change a circle fitting to a plane fitting. How? Plus ax2 plus ay2 plus b x plus c y plus d equals 0. Okay? Any type of circle. Circle is what? The geometric. This is called algebraic. The geometric is basically you have x minus xc, which is your center to the power of 2, plus y minus yc to the power of 2 minus r2 equal 0. Right? This is literally that. And the real geometric is basically the square root of this, minus r. So the real geometric fitting of circles is actually nonlinear, right? But we basically turn it into algebraic to make it linear. Now, and here basically if you expand this, you're going to get this with the exception that a is equal 1, but any multiplier of this would basically give you that. So it's going to be the same algebraically. Okay, so now we have something like this. How can I change this to make it into a plane fitting? We have how many? A, B, C, and D. Okay? So what I do is I create an extra variable called Z. That's going to be the third dimension, right? What do I put that Z as? Because if you guys remember, what do we had in terms of our plane fitting? AX plus B, or I'll do it this way. AZ plus BX plus CY plus D equals 0. How can I create that into this? So you add an extra dimension Z that is actually X2 plus Y2. Now this formulation is basically that. So you have A, X2 plus Y2 plus bx plus cy plus d equals 0. You put this as an extra dimension z. You perform the exact same thing. Now our x is going to be what? That x that we have is going to be zi or z1, x1, y1, okay, z2, x2, y2, and so on and so forth. You have n of these, right? N by 3. Perform the exact same eigenvalue decomposition. You get the A, B, C, and D exactly in the same way, subjected to A2 plus B2 plus C2 equals 1. So we've now transitioned a circle fitting in 2 dimensions, into a simple hyperplane fitting by changing a variable. That's basically what we're doing there, right? So our constraint is this, that is equivalent to hyperplane fitting to a 3 dimension by changing of our variables like this, which we talked about, by means of our z, basically, which is an additional dimension, being xi2 plus dy2. You can, once you get the a, b, c, and d, you can now basically change it and convert it into this form, which is basically our geometric understandings of it, yeah, because we need the mean and then the radius, right? By basically employing this, which is a simple substitution. So A is basically the center in X, B is the center in Y, and R is our radius of our circle, right? Now, why do we not always use this as a circle fitting? Well, there's an obvious problem here, right? And we're identifying an extra dimension as a function that is correlated with 2 other dimensions. So you're going to have some biases here. Okay, and these biases, and these show itself numerically in certain combinations geometrically through that particular circle. I'll also give you some examples of, for instance, different distance measures and how that would actually impact our final formulation in ellipsis. If you are trying to fit using this method on half a circle points, it basically gives you a biased result.